Let's explore 2 pointers. The trick behind solving array problems in seconds. Let's consider a common problem. Finding 2 numbers in a sorted array that sum to a specific target value. The most straightforward, or brute force, approach involves checking every single possible pair. This means for each element, we iterate through all subsequent elements. This method relies on nested loops, leading to a significant number of operations as the array grows. For an array of size n, this brute force method typically requires n squared, or O, of n squared comparisons. In a technical interview, such an inefficient solution would likely lead to a timeout due to its poor performance on larger inputs. However, there's a more optimal approach called the 2 pointers technique, which can solve this problem in just O of n, or linear time. This difference isn't just about speed. It's about recognizing inherent structure in the problem that allows for instant elimination of impossible answers. The 2 pointers technique leverages the fact that our array is sorted. This property allows us to make intelligent decisions that significantly reduce the search space. Instead of exhaustively checking every pair, we can strategically narrow down the possibilities. The key is to understand how the sorted order gives us clues about potential solutions, and how to use those clues to move forward efficiently. With the 2 pointers approach, we initialize one pointer, typically called L for left, at the beginning of the array, and another, R for right, at the very end. These pointers define the current search window. Because the array is sorted, this initial setup allows us to quickly evaluate the sum of the smallest and largest available elements. The core idea is to sum the values pointed to by L and R. We then compare the sum to our target. If the sum, in this case 1 plus 7 equals 8, is less than the target, which is 9, it means we need a larger sum. Since the array is sorted, the only way to increase the sum is to move the left pointer L to the right towards larger values. Moving R left would only decrease the sum further. By moving the left pointer L to the right, we now point to a new value. We repeat the process. Sum the new elements. 2 plus 7 equals 9. This time, our sum exactly matches the target of 9. This signifies that we have found the 2 numbers that satisfy our condition. The power of this approach lies in eliminating a large portion of the array from consideration with each single move. Once a match is found, the pointers highlight the solution pair. This method efficiently pinpoints the answer without needing to re-evaluate elements that have already been considered. The L and R pointers effectively meet or cross when the entire array has been searched, or a solution is found, ensuring we visit each element at most once. This final state clearly demonstrates the efficiency of the 2 pointers technique. Instead of n-squared comparisons, we only performed a handful of operations, visiting only a few elements. This confirms its linear time complexity, or O of n, making it ideal for large datasets and a strong solution in technical assessments. Understanding and applying patterns like 2 pointers transforms slow, nested loop solutions into elegant, efficient algorithms. So why does 2 pointers work? It all comes down to one thing. The array is sorted. When you start with pointers at opposite ends, you're holding the smallest and largest values. If their sum is too small, you know that pairing the smallest value with anything smaller than the current largest won't help. For example, if 1 plus 7 equals 8, and 8 is less than 9, you move the left pointer right, increasing the sum. If the sum is too large, pairing the current largest with anything bigger won't work either. For instance, if 4 plus 7 equals 11 and 11 is greater than 9, you move the right pointer left, decreasing the sum. Every move eliminates a whole set of impossible pairs. You're not guessing. You're using the sorted order to guarantee that once you move a pointer, you never need to backtrack. That's the core insight. We can see the progression. L equals 0, R equals 4, then L equals 1, R equals 4, leading to the solution where L equals 1, R equals 4, and a match is found. And because each pointer only moves in one direction, you visit each element at most once. This is visually represented by the search space grid, where each pointer movement eliminates entire rows or columns of potential pairs. This systematic pruning ensures that we efficiently narrow down the possibilities without redundant checks. That's why it's big O of n. To elaborate, since the L pointer moves at most n steps, and the R pointer moves at most n steps, the total moves are less than or equal to 2n. This means the algorithm completes in big O of n time, making it highly efficient for large datasets. Let's see this in code. We initialize two pointers. Left starts at index 0. Right starts at the last index. Then we enter a loop that runs as long as left is less than right. Inside the loop, we calculate the sum of the elements at the left and right pointers. If the sum equals the target, we return the indices. If the sum is less than the target, we increment the left pointer to increase the sum. If the sum is greater, we decrement the right pointer to decrease it. That's the entire algorithm. Notice that each iteration moves exactly one pointer, and we never revisit an index. This efficiency is why the time complexity is O of n. The loop runs at most n times, and each operation inside the loop is constant time. This is the template you'll use for almost every two-pointer problem. Initialize at opposite ends, compare, move based on the comparison, and repeat until you find the answer or the pointers meet. Two pointers isn't just for finding pairs that sum to a target. It's a general pattern that works whenever you have sorted or two-sided data, and you need to search, partition, or compare efficiently. For example, removing duplicates from a sorted array in place. You use one pointer to track the position of unique elements and another to scan ahead. When you find a new unique value, you copy it to the unique pointer's position and advance. The result? Order n time, no extra space. Or reversing an array in place. Start pointers at opposite ends. Swap the elements. Move both pointers inward. Repeat until they meet. Again, order n time. Order one space. The threesome problem, where you need to find three numbers that sum to 0, uses two pointers as an inner loop around a single outer loop, reducing order n cube brute force to order n squared. Even problems like container with most water, where you're finding the maximum area between two vertical lines, use two pointers to intelligently skip impossible candidates. The key is recognizing the pattern. Ask yourself, is the input sorted or can it be sorted? Does the problem involve pairs, partitions, or comparisons from opposite ends? Can I eliminate candidates by moving a pointer in one direction? Would brute force use nested loops? If yes, two pointers is likely the right tool. And once you see it, you'll start noticing it everywhere.